let this happen to you. Okay. A lot of this we've already covered in the context of nomenclature. So some of this is going to be review. The latter part of this chapter is not review, so that's where you're going to make sure that you have to read. Once again, as with Chapter 6 and Chapter 7, I'm going to encourage you to please read your textbook. We cannot cover everything inside this chapter in a single class session. All right, so why is it not cooperating? I guess I've got to start over again. My computer freezes sometimes when I open too long on these things. We are on Chapter 8. All right. Ionic, covalent, and metallic. We've already talked about ionic and covalent. Ionic is a transfer of electrons. You got a positive and negative thing that's holding it together. Covalent, you're sharing electrons, sharing valence electrons. Both of those types of bondings, the ionic and the covalent, are motivated by this octet rule. Ionic bonds, elements give up electrons, so they have an octet in their outer shell. Nonmetals gain electrons, so they have an octet in their outer shell. Covalent bonds are made so that they're sharing and the octet is in the same outer shell. And this is going to be super helpful when we get to molecular geometry. Metallic bonds are a little bit different. I think we talked a little bit about metallic bonds last week. It's sort of like a room full of jugglers, and everybody starts with 3 balls, and they're walking around and bumping each other, and at some point you might only have 1 or 2 balls, and at some point you might have 5 or 6, but you keep them all up in the air, and that's why metals make good conductors of electricity and heat, is because the electrons are held very loosely. All right, ionic bonding. Metals give up electrons, nonmetals take them. You can calculate the energy it is required to remove the electron from the metal, the ionization energy. You can calculate the amount of energy that comes back to you when the nonmetal accepts that electron, the electronegativity, but sometimes those numbers don't always add up to the same value. You would think the cost of removing and the cost of moving it from one place to another would give you the same amount of energy, and that's not necessarily the case. So what happens is this idea of the nuclear attraction between the nuclei of the elements taking up some of that last little bit of energy that is it's called the lattice energy. Lattice energy is a quantifiable value, and we generally discuss lattice energy when we're talking about ionic compounds. Remember, ionic compounds are crystal lattice structures that are repeating, and we use what's called the lowest whole number ratio, or the formula unit, to express. So you may have a crystal of sodium chloride that has 487 sodiums in it and 487 chlorines, right? You don't say Na487 Cl487. You use the lowest whole number ratio, which is NaCl. The energy that you use for this is dictated by Coulomb's law. So this energy here, the lattice energy, is related to Q1 and Q2. Q1 and Q2 are the charges of the individual ions, and D is the distance between the nuclei of the atoms involved in the bond. So, if you think about the energy that's required, this lattice energy, which is going to be this E value right here, K is a constant, it's a number that doesn't change, it just helps the algorithm behave. Q1 and Q2 are the charges on the ions involved. So let's think about that first before we move on. I'm gonna abbreviate the formula here. So E is equal to K, which is a constant, times Q1, Q2 on top, and D on the bottom. These are the charges on the ions involved in the ionic compound, and D is the distance between the nuclei of the atoms involved in the bond that is ionic. So let's think about that. So this is the total energy. This is the lattice energy, and that's the amount of energy in kilojoules per mole to separate 1 mole of any element. So for example, if we had NaCl and a crystal structure that went on and on and on, if I had 1 mole, or 6.02 times 10 to the 23rd of these units, the Na and the Cl, I could describe how much energy it would take to separate them as this lattice energy, and the units would be kilojoules per mole. One of the experiments that, I don't know if you still do in Chem 151, that what we used to do, is you take plain old room temperature water, and you put salt in it, and the salt dissolves, and it dissociates into the sodium ions and the chlorine ions. If you hadn't done that experiment before, and you know now that there's lattice energy involved, what would you predict is going to happen to the temperature of the water when you put the salt in and it is dissolved and broken up into its component ions? Is it going to go up, is it going to go down, or is the temperature going to stay the same? Actually, the temperature goes down. The temperature of the water decreases. So I take a beaker of water, I take the temperature, I add a whole bunch of salt to it, I take the temperature again, and the temperature of the water goes down. So in this case, what is the system and what is the surroundings that I'm talking about here? So I've got my water, and in I dump some NaCl. What's the system and what's the surroundings here? This is the system, and this is the surroundings, all right? So what's happening? Where's Q going? It's going from the water into the NaCl or from the NaCl into the water? If the temperature is going down. So the temperature goes down. The Q is going from the water into the NaCl. So that is a measure of lattice energy. If we weighed out exactly 1 mole of sodium chloride and we dissolved it in water, we could figure out what the lattice energy was as it dissolved. So the lattice energy is described by this equation. So if we're saying something, for example, like lattice energy of NaCl versus CaCl2, for example. When this breaks up, what are the ions that it's going to break up into? Na and Cl. What does this one break up into? Ca plus 2, and what else? And 2 of those Cl minuses. All right, so if we look back at the formula, the charges on the ions, if these numbers get bigger, what's going to happen to the overall lattice energy requirement? It's going to increase, right? Because if something that's on the numerator gets larger, the charges on the ions, for example, calcium ion versus sodium ion, it's going to take more energy to break up calcium, and that makes sense, right? Because it's got a 2+ charge. It's going to be harder to break something up that has 2 pluses on it than it is to break something that has only 1 plus on it. All right, let's think about the distance idea. As the distance gets smaller, so the elements are getting closer together in the lattice, that number is decreasing. What's going to happen to the energy requirement for lattice energy? It's going to go up. So the closer they are, the higher the energy requirement, the larger the charge on the ions that are being broken up, the larger the energy requirement. All right, I think there's a table on the next slide that shows that. Here we go. All right, if we look at lattice energy here, lithium fluoride, lithium chloride, and lithium iodide. All right. Lithium all has what charge? +1. Fluorine, chlorine, and iodine have what charge? -1. All right. Why does it take less energy to break up a mole of lithium iodide than it does to break up a mole of lithium fluoride? Who's bigger? Okay, if we look at fluorine, chlorine, and iodine on the periodic table, iodine is going to be the largest one, right? So the distance between the atoms is going to be larger for lithium iodide. If the distance is larger, what happens to the energy requirement? It goes down. All right, so it's all mathematically related. If we look at things that are, let's see here, charge-wise, let's see. We've got chlorine, MgCl2, and NaCl. Okay, Na and Mg are in the same row on the periodic table. They're both in row 3. Na is element 11, Mg is element 12. So they're in the same row, but NaCl only costs you 788 kilojoules per mole to break it up. MgCl2 costs you, holy crud, 4 times as much almost. So what's different about MgCl2 versus NaCl. Mg has a 2 plus charge, so you can see that the numerator is going to make the lattice energy larger. All right, so that gets us to this idea of what happens during these energetics of ionic bonding. So there's 3 different types of energies that are expended during this chemical reaction that happens. The first bit of energy, let's see, where are we starting out here? Well, you know what, that diagram, let's go to the next slide that shows. Here we go. When you break something up and you put it together, you would think that the overall energetics would be the same, but that's not the case. What happens is some of the energy is taken up by the electrostatic attraction versus repulsion of the nuclei that are next to each other. Now there's 2 diagrams here that show you 2 versions of what is the microscopic perspective of what's happening in the elements here. So if we look at this, so this might be a crystal of sodium chloride. So we've got sodium here, and chlorine here, and chlorine here. So these are attracted to each other, right? That's what's holding sodium chlorine together, because sodium is positive and chlorine is negative. However, the chlorines and the chlorines are repulsed by each other because they're negatively charged. So there's conflicting charges going on in the same compound. If you looked at the distribution of potential places where an electron could be, if each one of the points in this bottom diagram was a probability point of where an electron could be in the context of a bond between 2 nuclei, and so that's a nuclei there, that's a nuclei there, you can see that the majority of the electrons are going to be hanging around the individual nuclei. The density is much higher in between them, and then as you get further and further away, the density decreases. So you've got attractions and repulsions that scoop up some of that energy that's not accounted for when you break the bonds and then reform them. So those are ionic bonds. We talk about ionic bonds in the context of losing or gaining electrons. Now, covalent bonds are between different kinds of elements. Ionic bonds are between metals and nonmetals. Covalent bonds are between what? Non-metal combination. So in covalent bonds, you can have 2 types of covalent bonds. You can have polar covalent bonds, and you can have non-polar covalent bonds. All right, what might be the difference between polar and non-polar covalent bonds? Well, remember the chart of electronegativity, so the trend that we talked about in the last chapter about electronegativities, and it has to do with how greedy elements are for the electrons of other elements. So electronegativity and ionization energy follow the same trend, and it's opposite of the trend for size. And so I always make my arrows on the order of the increasing side. Let's see if we can get this to focus a little better. All right, so if we look at this idea of covalent bonds being either polar or nonpolar. What does polar versus nonpolar mean in the context of science? Has an unequal charge. So polar has an unequal charge distribution, and nonpolar has an equal charge distribution. All right, things that are nonpolar have the same electronegativity. If they're polar, they're going to have very different electronegativity. So, for example, if you've got 2 elements that are hooked together that are the exact same thing, like when we get to molecular geometry next week, we'll see that the N2 molecule has a triple bond between it. Nitrogen and nitrogen has the exact same electronegativity, so they're not going to be sharing those electrons between them very unequal. They're going to be sharing them very equally because they both have the same pull. Conversely, if we look at something like water, right? Water looks like this. We've got 2 non-bonded pairs of electrons here and then 2 bonded pairs. The bond that exists between oxygen and hydrogen, who is more electronegative between oxygen and hydrogen? Oxygen is way more electronegative. So what happens is you'll see in the textbook they're going to use some symbols like this to show that the sharing in the context of this bond is unequal, that oxygen is much more greedy for the shared electrons between them than hydrogen is. So they say that this has a partial negative charge and this side has a partial positive charge. So different electronegativities are polar covalent, same electronegativities are non-polar covalent, and that's the big difference between the two. Here in this diagram, they're showing you the difference here in terms of electron cloud. Here's F2. It's very nonpolar. The electron cloud is shared very equally. Here, HF. Who is more electronegative? Hydrogen end of it or the fluorine end of it? The fluorine end of it. So you can see that the red area, which has more electrons, they're symbolizing in this diagram, showing more electrons on this side than on this side, so it's shared unequally. All right, so it's called a bond dipole. That's different than a polar molecule. It is a dipole based on a bond, and a bond is between two elements in a compound. We're going to talk about molecular polarity in the next lecture. So there's our trend in electronegativity that we've already discussed, and polar covalent bonds. All right, now we've got to learn how to draw Lewis structures, and since scientists are so egocentric, who do you suppose came up with this idea of Lewis structures? Mr. Lewis, most likely, and it's usually white males that like to name these things after themselves, right? All right, so we'll think of that. You know, if you discover a new element, you get to name it after yourself, or you get to name it where it was discovered, or you get to name it after somebody that was famous. Like there's Einsteinium. Well, he didn't discover Einsteinium, but they named it in honor of him. There's Californium. Where do you suppose they? California, right? I always thought if I was going to discover a new element, that woodium doesn't really work, right? Woodium. But my first name is Lorelei, and I thought laurelium would be a good element, wouldn't it? Wouldn't laurelium be a good element? I like that. So if any of y'all win the Nobel Prize in chemistry and you want to honor your first and most favorite chemistry teacher ever, right, by naming an element after her, laurelium is an excellent name. All right, so Lewis structures, we're going to go back to not being egocentric. Lewis structures you have to draw before you can learn how to draw molecular geometry. All right, so here's the set of rules. You got to determine the number of valence electrons. And what I'm going to do is I'm going to go through the rules real quickly, but then using the rules as a backdrop, I'm going to go through some examples. All right, so you got to determine the number of valence electrons. Now, representative elements, the group A elements, the 2 groups on the left and the 6 groups on the right, how do you know how many valence electrons they have in their shell? It's the same as the group number. So for example, sulfur is in group 6. How many valence electrons does sulfur have? 6. Okay. Lewis structures, generally we're going to write for covalent compounds because those are the true molecules. Remember, ionic structures are crystal repeating structures, so we don't really talk about the molecules because there's not true molecules, so we're discussing Lewis structures in the context of covalent compounds, non-metal combinations. So that's why it's easy to figure out where their valence electrons are. So the central atom is usually the least electronegative element, so that's where your trend is going to come in. Generally, the most likely elements are going to be carbon first as a central atom, then nitrogen is going to be second most likely, then oxygen, and we'll talk about why in just a minute. Fill the octets of the central atom. And so let's go through these rules. I'm going to summarize the rules a little bit differently on the ladybug as we go through some examples. All right. So Lewis structures. So I'm going to use the rules here, and then we're going to go through the rules. Number 1, count valence electrons. All right, I'm going to abbreviate a lot of the rules. Number 2, determine, and I'm going to abbreviate, determine the central atom. It's either most electronegative, or generally it's in this order: carbon, nitrogen, and then oxygen. So that's the first most likely, that's the second most likely, that's the third most likely to be the central atom: carbon, nitrogen, or oxygen. Third step, distribute peripheral atoms around the central atom. Use bonds. So for one bond equals 2 electrons. So you're going to subtract 2 electrons for every bond. And the last step, distribute remaining electrons so that all elements except hydrogen, helium, and so hydrogen and helium have an octet. All right, I'll let you write all that down, and then we're going to go through. Distribute the remaining electrons so that all elements, except for hydrogen and helium, have an octet of electrons. So write all those down, those rules, and then we're going to go through some except for hydrogen and helium. All right, so using those rules as the backdrop, we're going to do it one at a time. And we're going to start with, let's see, we'll start with CH4. Anybody know what CH4 is? Methane gas, right. It's a greenhouse gas, bad for the planet. Fart gas is what it really is, right? And you ever been in Boy Scouts? You know you can light these? You ever tried that? Come on, fellas. I know you have. I raised 2 sons. No? What the heck? All right, so there's a Boy Scout in the audience. Yeah, you can burn yourself pretty bad, so be careful. CH4 is a greenhouse gas. What is the #1 producer of methane gas on the planet? Do y'all know? Cows. They're number 2. They have a lot of flatulence, those cows, because of their digestive system. They have to ferment the stuff that they eat. But there's actually something much smaller than a cow that's the #1 producer of methane gas. Termites. Termites. They have the same digestive system basically as a cow that has to go through fermentation. They eat the wood, and they produce a lot of methane gas. So if we could figure out a way to harvest methane gas, it's a very clean burning fuel, right? Either from cows or termites. I don't know how you do that. Little tiny tubes for the termites, right? All right, let's do the Lewis structure and stop talking about termite farts. Carbon. How many valence electrons does carbon have? 4. Hydrogen has how many valence electrons? 1, and there's 4 of them, so that's a total of 4. That gives me 8 valence electrons, all right? So I counted the valence electrons, I added them up. Now I got to determine the central atom. What's going to be the central atom there? Carbon, all right. Put that one in the middle. Now I'm going to distribute the peripheral atoms around the central atom using bonds. 1, 2, 3, 4. Hydrogen, 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 hydrogen. I want to make them as symmetrical as possible. 1 bond is 2 electrons, so I got to subtract 2 electrons from my total for every bond that I make. 2, 4, 6, 8 minus 8 gives me 0. So I don't need to distribute any electrons, and it's fine. Let's back up a little bit. Let me show you some rationale for this. Let's look at Lewis structures for individual atoms. I don't think we've talked about this at all. When you're writing Lewis structures for individual atoms, this is going to be the symbol for the element. And then you're going to put the electrons in one of 4 areas, and it starts on one side and it goes all the way around, and it starts over here. So it goes 1, 2, 3, 4, 5, 6, 7, 8. And that's because electrons are paired as they're going around it. So if we look at hydrogen's Lewis structure, how many valence electrons does hydrogen have? 1. There's the Lewis structure for lonesome little hydrogen. Carbon, on the other hand, what's the Lewis structure for carbon? It's got 4 valence electrons, so now I'm going to put 1, 2, 3, 4, right? So it makes sense that when hydrogen comes up here and wants to bond with carbon, that valence electron now is going to be here. Hydrogen is going to bond with carbon, and both of these electrons now are going to be circling around both of the elements. They're going to be circling, spending more time around carbon because carbon is more electronegative, but they will spend some time around hydrogen. And this one does the same thing too. So they circle around both things. So when you have a Lewis structure for an element, that means there's 2 electrons, one of which was donated by the hydrogen and one of which was donated by the carbon, because it has 4 opportunities to bond. Now, another word of caution. When you're looking at the individual Lewis structure of an atom, you can only bond where there are non-paired electrons. So if we look at carbon and we compare it to nitrogen's Lewis structure, how many valence electrons does nitrogen have? Nope. 5. 1, 2, 3, 4, 5. How many opportunities to bond does nitrogen have? 3. Oxygen, how many valence electrons does oxygen have? 1, 2, 3, 4, 5, 6. How many opportunities to bond does oxygen have? Only 2. So just because you have more electrons doesn't mean you have more opportunities to bond. They used to call organic chemistry the study of carbon-based compounds because carbon is the thing that makes the most bonds of any element on the periodic table. First of all, it's super electronegative because it's very small, and it has 4 valence electrons, each of which has the opportunity to bond. Yes, question?
I noticed with oxygen on the very bottom, it didn't exactly follow the diagram.
Well, close enough. 1, 2, 3, 4, 5, 6, 7, 8. You want to know paired versus non-paired.
Yeah, but it doesn't matter.
As long as you have 1, 2, 3, 4, 5, 6.
Yeah. Oh.
Okay, so it doesn't have to be in the exact same spot, but
No,
you do
I
have to
get it.
start
I'm
on one
just
side.
making sure.
Right. Okay, so that makes sense that carbon would be most likely to be a central bond, nitrogen would be atom, and so on, because this has got 4, this has got 3, and this one has only 2 opportunities to bond. So that's why that particular thing happens. Okay, so if we're going back down now to the next example, let's try NH3. What's the common name for this stuff? Ammonia. Okay, ammonia. So let's count the electrons. How many valence electrons does nitrogen have? 5. Each hydrogen has 1. There's 3. That's 8. Now, they don't always have 8. I'm just using super simple examples at the beginning here until we get a little bit more complex. 8 valence electrons. Who's going to be the central atom here? Nitrogen. 1, 2, 3. Hydrogen, hydrogen, hydrogen. How many valence electrons do I have to subtract now from my total of 8 for those 3 bonds I just made? Minus 6 gives me 2 left. Now I have to use my last rule, distribute the remaining electrons so that all elements have an octet. Where am I going to put those last 2 electrons? On the nitrogen. And here's why. Because each of those hydrogens is full with an octet. That hydrogen thinks both of those electrons belong to it. Each of those, that's not an electron there. Each of those hydrogens considers itself full because it's got 2 valence electrons, and hydrogen and helium are always good with 2. Nitrogen considers all of those to be belonging to it. So nitrogen has 2, 4, 6, 8. So now they all have their octet. Let's do another example. Good old H2O. How many valence electrons does each hydrogen have?
2.
Well, there's 1 each. There's 2 of them. How about oxygen? 6. Once again, they don't all have 8. I'm just using some super simple examples here. Who's going to be the central atom, hydrogen or oxygen?
Oxygen.
Can hydrogen ever be a central atom? Why not? It can only bond in one place. Hydrogen and helium can never be central atoms because it's like a one-armed fella, a one-armed girl, right? All I can do is hold on with one hand. All right, so we're going to put oxygen in the middle. We're going to put the 2 hydrogens on each side. How many should I subtract from my 8 now for those 2 bonds I made? 4. I got 4 left over. Who needs those last 4 electrons? And I'm going to put them as paired because oxygen's individual Lewis structure looks like that, right? So where do the bonds occur? Here and here. And so I have to put the remaining electrons as paired electrons because that signifies to the observer you cannot make bonds there, right? So now if we're looking at this water molecule, hydrogen is happy, it's got its full outer shell, and oxygen thinks it has an octet because it's got 2, 4, 6, 8. So that's why covalent bonds happen. Now, let's think about the bonds themselves as either being polar or non-polar. Let's look at this one right here. Methane. Is the bond between carbon and hydrogen polar? Who's more electronegative, carbon or hydrogen? Carbon is way more electronegative, so who's going to be pulling on those electrons tighter? Carbon, so the electron is going to be going in this direction, right? They're all going to be pulled in. What about this bond? Is this a polar bond? Nitrogen and hydrogen? This bond right there, is that polar? You bet it is. Who's going to be more electronegative? So we're going to show the electrons going from hydrogen being pulled by nitrogen. Same thing here. Who's going to be holding on to those electrons tighter that they're shared? Oxygen. So you'll see in the textbook they're going to put that little symbol that shows you that it is a polar bond. It's different than a polar molecule. We'll talk about polar molecules next week. So there's your Lewis structure. Good ways to practice. Make sure that you've got an octet. Now, if you don't have enough electrons, what you have to do is double bond. For example, let's see, HCN. Let's do this one on the ladybug so that we can see how that works. HCN. HCN. All right, we'll use our rules here. How many valence electrons has H got? 1. How about carbon? 4. Nitrogen has 5. So we got 10 total. Who's going to be the central atom here? Carbon for sure, right? How many am I going to subtract now from my total of 10? Minus 4, that leaves me 6. All right, does hydrogen need any more? No. How many more does carbon need? It's got 2, 4, so it needs how many more? 4. And how many more does this nitrogen need? 6. Well, crud. We need 10. How many we got? 6. So now you double bond. Am I going to double bond here? Heck no. Why not? Hydrogen can't do that with only one arm. So we're going to throw a double bond there. So now I have to reevaluate all this. I have to subtract 2 more. Why am I subtracting 2 more? That's for the double bond, right? I have to take off of that one. So now I got 4. So now let's reevaluate the situation. Hydrogen still doesn't need any more. Right now, this carbon thinks it has how many? 6. So it needs how many more? 2. Right now, this nitrogen thinks it has how many? 4. It needs how many more? 4. I need 6. All I got is 4. What's my option? Triple bond. Am I going to put it there? Heck no. I'm going to put it there. I got to subtract 2 more. That's for the triple bond. Now I got 2 left. Hydrogen doesn't need any more. Does carbon need any more? Nope, carbon's good. How about nitrogen? Needs 2 more. Where am I going to put them? The rule is the electrons are going to be repulsed by other electrons, so they want to be as far away from each other as they possibly can. So, yes?
I don't understand why that 4 and the 6 for the carbon and the nitrogen. Like why?
Right here?
Yeah.
Because when I originally did it like this, and I was evaluating how many more each one needed, this one didn't need any more. This one needs 4 more.
To get the octet?
To get the octet.
Oh, okay.
This one needs 6 more to get the octet. So that's, is that what you were asking me, is where those numbers came from? Thank you for asking that. All right. I know I go through this kind of fast, but I will also post this after class is over so that you can look at it. Resonance has to do with a particular bond being able to move from one place to another. For example, O3, and what is O3? We talked about O3 already in this class. What's O3? Ozone. All right, so let's look at ozone. Ozone has what we call resonance. Look at O3. Each oxygen has 6. 6 times 3 is 18. Minus 4 leaves me 14. So 6 more I need here, right? I need 4 more there. I need 6 more there. So 6, 12, 13, 14, 15, 16. I only have 14, so I'm going to double bond. Minus 2 gives me 12. Now, this one needs 6. This one only needs 2. This one needs 4, so we're good. So 1, 2, 3, 4, 5, 6. 1, 2, 1, 2, 3, 4. So that's what ozone looks like. Resonance means that this double bond sometimes is between these 2 oxygens and sometimes it's between those 2 oxygens. It's not a different molecule, one that has it here and a different one that's there. It's the fact that that double bond can move. That's what it's called resonance. For example, if you were a guitar player, and here's my really bad drawing of a guitar, and you've got the strings that go across the hole here, and you got the thing that has the frets on them where you tighten the strings. When you pluck one of these strings, what would you see it doing? It's going to vibrate. So it's going to go this direction and that direction multiple times. It's going to go back and forth. That's exactly what happens in a molecule. That double bond can move back and forth. So there are two different resonance forms. That's one resonance form. The other resonance form would be that. You will have to on the quiz and on the exam describe the different resonance forms and how many each molecule could potentially have. We'll finish this discussion on Thursday. What's today?
Tuesday.
Thank you. We'll finish this on Thursday. Yes.
I know double electrons with the middle oxygen have to be treated another bond
Because then you're going to run out of electrons.